All right, we're back here, Physics 1151. It's Thursday, last day of the week for physics class at least. And we're going to finish off our discussion of Chapter 19 by discussing the three ways in which heat can be transferred between objects or between media. And we've already discussed a fourth way, latent heat. Remember, for example, I boil the water, I evaporate the water here. The latent heat goes into vaporizing. This water will go and condense this onto a cool surface, and it will transfer the heat to the surface. That's an example of latent heat. The other three mechanisms that we're going to describe today are what are called conduction, convection, and radiation. And they're all apparent from this boiling pan of water. So radiation is electromagnetic energy radiated by the burner. And I don't need to be in direct contact with the burner. I feel it. It's hot, right? And this is glowing. So there's a lot of electromagnetic energy radiated, and it doesn't need a medium, and that's transferred from the burner through the air to my hand. And so that's one example, is through the transfer of electromagnetic energy. That's called radiation. Okay? Now the second mechanism, if I put two surfaces in contact, say the burner and the bottom of the pan, and the pan contains water, the burner's at a higher temperature. And so the burner is going to transfer energy by direct contact to the bottom of the pan, and the bottom of the pan is in direct contact with the water, and that transfer by direct contact is called conduction. And the third mechanism, so the bottom of the water is heating up, it's getting heated directly, but then you have these currents that are produced inside the water, inside a fluid, and those transfer the heat energy from the bottom of the water to the top, and you form a little conveyor belt here of circulating energy in a fluid, and that's called convection. Let's look at conduction first here. So I have two types of material. I have a metal straw and I have a wooden chopstick. And I'm going to stick both of them in the hot water. What's going to happen here? My right hand, it feels hot, right? This metal straw is hot. So heat is transferred through conduction very rapidly through this material, the metal straw. But I can keep my hand on the wooden chopstick for much longer. So conduction, the transfer of heat from the hot water to the chopstick, to my finger, must be slower when I'm transferring it through some materials like a wooden straw, whereas with a metal straw, the heat is transferred very rapidly. And so I perceive this is hotter. Heat is transferred more rapidly through a metal than a chopstick. Okay. Now I have a beer glass here, and I have some ice. What's going to happen if I stick the chopstick and the metal straw into the ice? Well, give it a minute. The metal straw feels cooler than the chopstick. What's happening here? Well, my hand is at a warmer temperature than the ice, and one end of each is in the ice, and the other end is touching my hand. And so energy is being transferred, the heat is being transferred from my hand, the warmer object, to the ice. But I lose more heat through the metal straw because it can carry away the heat more rapidly than the wooden chopstick. And so some materials, like metals, are very good at transferring heat through conduction from a hotter body to a colder body, while other materials like wood, the wooden chopstick, don't transfer heat as rapidly from a hot body to a warm body. And so this is called conduction. Conduction is the transfer of heat from a warmer body to a colder body by direct contact. So the straw is in direct contact with my hand. Okay, so we're on our last set of notes for Chapter 19, which is heat transfer mechanism. And we just did a demo with mainly conduction, one method of heat transfer. So what's going on here with conduction? So we saw in the demo that conduction is the transfer of heat directly through two materials that are in direct contact. So in other words, the burner is in direct contact with the bottom of the pan. The bottom of the pan is in direct contact with the hand. Or in the demo, the water was in direct contact with the chopstick, and the chopstick was in direct contact with my hand. So you have to be in direct contact, and you have to have a temperature difference to get a heat transfer by conduction. And we saw that heat is more rapidly conducted through a metal, the metal straw, than it was through the wooden straw. So some materials are better conductors of heat than other materials. So at the molecular level, what's going on here is you're heating one end of the material, and the molecules or the atoms can vibrate. And if they're warmer, they vibrate very fast, and they smash into the molecules next to them, which aren't as warm, and they're vibrating slower, and they transfer some of their molecular energy. And then these molecules they smash into these molecules, and they transfer energy. And so energy gets transferred along the material, or in our case, it was the metal straw and the chopstick. And metals can transfer this energy much more rapidly and efficiently than what's called insulators, like wood. And so these materials are called thermal conductors, the metals, and the other materials like wood are an example of thermal insulators. And so the material itself affects the ability for the heat to be transferred between a warmer body to a colder body. So now there's other variables that also come into play here. And so let's consider a warmer body. So you have two ends here, and you have a metal bar in between. And one end of the metal bar is in contact with a cooler body, and the other end of the metal bar is in contact with the warmer body. And let's assume that we place some insulation around the sides so we don't lose any heat from the sides, so that the only heat being transferred from the hot body to the cold body is by conduction through the metal rod. Okay, so what factors influence the amount of heat that's going to be transferred? Well, we just saw in the demo that it depends on material, right? So some materials like metals are very good conductors of heat, and others like wood are not. Okay, so it depends on the material that this bar is made out of. It obviously depends on the time in which the conduction is taking place, right? If we keep the bar in contact with the two bodies for a longer period, there's going to be more heat transferred from the hot body to the warm body. The amount of heat depends on the temperature difference, right? The bigger the temperature gradient between the warm body and the cold body, the more heat will be transferred through the metal rod. So it depends on the temperature difference, and that's positive. So larger temperature difference, more heat transfer. Longer time, bigger T, more heat transfer. Bigger conductivity, more heat transfer. Cross-sectional area of the bar. So in other words, you can think of this as the diameter if it were a cylinder. So larger diameter, you're going to transfer more heat, right? There's a greater cross-sectional area that's in contact with the warmer body and the colder body. So bigger area is going to be more heat transfer. What about length of the bar? If we increase the length of the bar, is that going to increase the conduction of heat, or is it going to decrease it? Well, if we go back to our molecular model, if you have a longer bar, it's going to take more time, right, for these molecules to smash into each other and to transfer their energy all the way to the other end of the bar. And so
unlike these other variables, larger length will decrease the conduction of heat. And we can put all of these together into a mathematical equation to determine the amount of heat, Q, transferred in a time t. It depends on the conductivity, the thermal conductivity of the bar, of the medium. It depends on the area, the cross-sectional area. Depends on the temperature gradient, the difference between the warm body and the cold body. Depends on time. And L is in the denominator. Longer bar, less heat transfer. And so this gives us the equation for the amount of heat transferred. Now, more often than not, we want to know about the power, the heat transferred per time. So we can divide both sides by T, and energy over time, Q over T, is the power. And it depends on the conductivity, the area, the temperature gradient, and inversely proportional to the length. And since the whole right-hand side must have dimensions of energy per time or joules per second, we can push all these other variables to the other side, and we see that conductivity must have units of joules per second per meter per degree Celsius. So kind of a weird unit, but you should be able to look at this equation and know the dimensions of the other variables and be able to, from that, get the units for the conductivity. And the main thing to remember is that a bigger number for conductivity means a better conductor of heat. So let's look at some examples here. Well, metals have big values for conductivity: aluminum, brass, copper, silver. So those are very good conductors. Gases are pretty bad, right? Air is a very poor conductor of heat. So you don't get a lot of heat transfer through air by being in direct contact. So air is a poor conductor, good insulator. Then you have other materials. Diamond's a good conductor. Glass is a good insulator. The conductivity is low. Water's a fairly good insulator relative to metals, but water's a much better conductor relative to air. And so low numbers, wood, wool, styrofoam, those are what are called insulators. Those are insulate from heat. They don't allow much heat transfer. And so the bigger the number, the higher the conductivity, the better the material conducts heat. So let's look at a couple questions here. So suppose you step out of bed in your bare feet on a cold morning, and is the ceramic floor going to feel colder than a carpeted floor, or is it going to feel warmer than a carpeted floor? Okay, and I think we all know that a ceramic tile floor feels colder than carpet when you're standing barefoot. So why is that? Well, ceramic is a better conductor than carpet. They're not in this table, unfortunately, but ceramic has a higher conductivity than carpet. And so ceramic is going to conduct heat away from your warmer foot to the cooler floor more rapidly than the carpet. Carpet is not as good as transferring heat. And so when you're losing more heat, the tile floor tends to feel colder. You're transferring heat from your hand to the floor. It's also why if you touch a metal doorknob, the metal will feel colder than if you touch an insulated doorknob, okay? Because the heat is transferred more rapidly from your hand to the metal. And so even though you can have a metal and an insulated doorknob and at the same temperature, the metal doorknob will feel colder. It's conducting heat away from your hand more rapidly. Okay. Here's another practical application. Which type of window will you get a larger heat loss due to conduction? So suppose you have two choices. You can buy a window which is a 1 centimeter thick chunk of glass, or you can buy a double pane window consisting of two 3 millimeter glass panes with an air gap in between. Which one is going to insulate the room better from heat loss to the outside? And the answer is the double pane window. And it turns out that stale air, if we go here, stale air, non-moving air, has a really low thermal conductivity, about 30 to 40 times less than glass. So an air gap in between two chunks of glass is a super insulator, okay, because stale air is a very poor conductor of heat. And that's the whole point of double pane windows, is you have a gas in between two glass panes, and that is a better insulator than if you just have the same thickness of a chunk of glass, because stale air is a very poor conductor of heat. Here's another example. If you have trapped air spaces, okay, so for example, like styrofoam with these little air gaps, or foam insulation where you have little pockets of air, that stale air again is a really good insulator. And so stale air, these little air pockets in between an insulating material really minimize heat transfer by conduction. So these dead air spaces are really good thermal insulators. So that process is called conduction. And conduction is the main method by which heat is transferred in solids. Okay. So what about with fluids? Well, when we were heating up the pan before, we saw these convection currents, right? So the burner was in contact with the bottom of the pan, and that heated up the bottom layer of the water. So what happens then is that in the fluid, you start to get these currents, and these currents carry the heat from the bottom, and they redistribute it. So the warm water rises. It's a little dense than the cold water, less dense, and that transfers the heat up here, and then the cold water fills the place of where the warm water is, and then that gets heated and rises. And so you start to form these little convection currents which transfer heat in the fluid. So convection is the transfer of heat by a moving fluid. So the fluid carries away the energy, the heat, and redistributes it. So it's not direct contact, but rather it's a moving fluid going across a body, and that carries away the heat. So let's look at how that happens here. So if you recall, we talked about buoyancy, right? So something will rise in a fluid if it's less dense than its surroundings, and it'll sink if it's more dense. So let's look at this heater. Suppose we have a baseboard heater here, and that's near the floor. So we're going to heat the air directly in direct contact with the heater. That's going to heat, and that air is going to be less dense than the surrounding air. So if we go back to our ideal gas law, PV is nRT, and the pressure really is pretty constant in a given room. If the height change in a gas is not large, the pressure is relatively constant. And so V over T is equal to N over R over P, and these are all constants. And so if you heat the air, larger temperature, then the same mass of air will occupy a larger volume. In other words, it will be less dense than the surrounding air. The same mass, bigger volume, lower density. So we heat the air here, it warms up, it becomes less dense than the surrounding air, and warm air rises. Okay, that forms the basis of a hot air balloon, right? Warm air rises, cold air sinks. So this warm air will rise, cooler air will drop and fill the void where the warm air is. That will get heated and rise. And the cooler air from here will drop and fill the void. And you start to form these convection currents where the heat is being transferred through the air, the gas, almost like a circuit, right? So you have air in a moving fluid, and that transfer. So a moving fluid carries away the heat, and this forms the basis of baseboard heating. And it's just due to these density fluctuations where the warmer the air, the more buoyant it is, and then it rises and cold air sinks, and you form these convection currents. And that's what was happening here with the water in the stove. You were heating the bottom of the water, and so that became warmer than the top, and the warmer water is a little less dense, so that rises. The colder water is more dense, it sinks, and you start to form this convection currents. And this is basically a conveyor belt, which is transferring this energy from the burner to the entire volume of fluid. So again, convection is the transfer of heat in a fluid due to a moving fluid. Currents. Here's a similar example to the pan, although it's not so obvious why at first. So why in the summer do we tend to get more thunderstorms and more clouds in the afternoon on a hot day? So you can have days where it's it's pretty clear in the morning, and then in the afternoon you get these cumulus clouds building up. So again, it's the same principle here. The sun heats the surface. And so the surface warms up, and around noon, around 12 o'clock or late morning, early afternoon, the surface starts to get pretty warm. And when it's warm, it becomes a little warmer than the air that's in contact with it, and it transfers by conduction the heat to that lowest level of air right next to the surface. Well, that warm air is less dense than the surrounding air, and so warmer air tends to rise, and you get this transfer of this energy upward. When it rises, it expands. When it expands, it cools. If there's moisture, the cool air condenses, it saturates, and you get cloud formation. And if you get enough water, you get rain. And so this basically is a very similar mechanism to our little example here where we're heating the pan of water. So this pan of water, the heating, is a nice example of natural convection. Here's another example, again with baseboard heating. So here's a question to think about. These baseboard heating units usually are mounted on the wall next to the floor, okay? Whereas these cooling coils and refrigerators are typically mounted toward the top of the refrigerator. And each of these designs, placing the baseboard heaters near the floor and placing the cooling coil near the top of the refrigerator, are designed to maximize the production of these convection currents. Why? Why would we want, let's look first, why do we want the baseboard heating unit near the floor and not near the ceiling? Okay. So stop your video, think for a minute here. Okay, now we're back, and it's just that buoyancy thing again, right? So if we put the baseboard heating it near the floor and we heat this air up right next to the baseboard heater, it's going to be less dense and it's going to rise, right? And we want it to rise, right? And then the cold air sinks, because then we get this circulation of heat, this transfer of heat, and we circulate it through the room. If we put the baseboard heating up near the ceiling and we heat that area, that's already it's less dense than its surrounding. It can't really rise anymore. So you're not going to get those air currents, you're not going to get those convective currents to transfer the heat. So we want to put the heating near the floor so that we can heat the air next to it. It'll rise, and then the cool air will sink, and then we form these currents which transfer the heat from the heater throughout the room. So now let's look at the cooling coil, right? We want to cool the refrigerator here. So what's happening here? Well, we're going to cool the surrounding air that's next to the coil, and cold air sinks, right? Warm air rises, cold air sinks. So now this cold air is going to sink. Warm air from the other part of the refrigerator is going to is going to take its place, and that air is going to get cooled, and then it's going to sink. And so we're basically forming a conveyor belt going in the opposite direction. And so that's why the cooling coils are near the top of the refrigerator, and that's why the baseboard heating unit is near the bottom, is near the floor of your room. They're both designed to maximize these convection currents, which either carry heat away from the baseboard heating or which remove heat from the refrigerator, right? They cool the air. So sometimes natural convection is not enough, and we have to force this flow. So we need a pump. In other words, we need to force the air to move through a system. And here's one example of an athlete. And you have a pump here, and you circulate this cool fluid, and it goes around his hand, and energy is transferred from his warm hand, to the cool fluid, and then that circulates through. So now you have warm water coming down, that gets cooled here, gets pumped back up, and so this cool water carries away heat from the athlete's body, and that's an example of forced convection. You're actually forcing this fluid through with a pump. And it's very similar to a radiator in your car, which carries heat away from the warm engine through a moving fluid, a coolant. The coolant circulates through the engine block, carries away the heat generated by the engine. You've got this pump which forces the fluid through, goes through this radiator which has the fan running, and that fan, through convection, dissipates the heat, kicks out the heat, and then you have this cool. So basically you have cool water going through the engine, and that carries away the heat by forced convection. So here's an example. Here's a little short video. We will end today.
There is nothing worse than snuggling up to a man that smells like this. This goop totally.
All right.
In this video, I'll be explaining how a radiator works and how it cools your engine. Now, a radiator is a pretty simple device. You're going to have an aluminum mesh, and in this aluminum device, there's going to be a tube that runs parallel through it all the way down, and it's going to come in with hot water, and it's going to come out with cool water. Now, how it does that is air is going to be feeding through this, and there's going to be aluminum fins attached all to these tubes here, and so it's just going to look like an aluminum mesh. Now, after that air passes through, it's going to cool these aluminum fins, which are connected to these tubes. Now, these coils are going to be full of coolant, which is going to be very hot from the engine. So they're going to give off heat to this aluminum, which is going to be cooled by the air, and so the coolant is going to come out cooler than it entered, and then go back to the engine. So here's how it's set up. You've got your radiator here in the front of the car. Now, the coolant is going to be running through. Here's your engine, here's a water pump, and here's a thermostat. So what happens is your car is going to start, and you're going to be running coolant through the engine here. Now, as this warms up, it's going to pass here, go through your radiator, cool down, and then go back into the engine. Now, when your engine starts, it's going to be cold, so you've got a thermostat right here. Now, what this does is, as you've got coolant running through, it looks at the temperature of it. Once the temperature gets too high and your engine is warmed up, then it'll pass the coolant back through the radiator, and then it'll come cool through the radiator, the cool fluid will come back to the water pump and then be pumped out back into the engine. Now if you turn your heater on, it's going to open up a valve right here, and that's going to allow this coolant to come in. It's going to be hot, and it's going to come through basically another radiator, and you're going to blow a fan on that, so this hot air, the air passing over this is going to heat up and then go into your car. Now, so that's going to come out, and then it's going to cool that coolant, and that's going to go straight back to the water pump and go back and recirculate through your engine. So what you do here is, as you have combustion, it's going to heat up your engine. Now your engine's going to create a lot of heat, and that's going to heat up the coolant. So the energy is going to transfer from the engine to the coolant. Then your coolant is going to pass through the radiator, and it's going to attach to these aluminum, well, it's going to give off heat to the aluminum, and since aluminum has a high thermal conductivity, it takes the heat very quickly. Now that heat is then passed to the air. As you're driving, you've got air flowing across these coils, and it's going to cool down your radiator, so it's going to cool down the coolant that's gone into it, therefore cooling down your engine.
T-Mobile is now America's largest.
Okay, so this is we're gonna end here today. We will finish chapter 19 with the last mechanism for heat transfer on Monday, and that's called radiation. And we saw a little bit of that with the burner. And radiation's a little bit of a different bird than conduction and convection, because with convection you need a fluid, like an air or a liquid. With conduction you need a solid material or a fluid in direct contact, the portion of the fluid in direct contact with the block. Radiation can be transferred without a medium, so that's a little bit different. We'll cover that on Monday, and then that is going to finish chapter 19, and then we're going to move on to chapter 21. So have a good weekend.